Mr. Heffernan here. Here's a video on centripetal motion and universal gravity. So universal gravity is the attraction of any mass with any mass in the universe. So in this case here, the Sun produces a force of gravity attraction on the Earth, and the Earth causes an equal but opposite reaction, force of gravity, on the Sun. So the gravity of the Sun on the Earth provides a centripetal unbalanced force, which provides the Earth's orbital motion. So universal gravity, all matter is attracted to all matter. Gravity is pretty weak though, so you won't even notice it until you have something really massive like a planet involved. And Sir Isaac Newton developed the formula we're going to use in 1687. So you got your mass, big M, and your small mass, little m. And the formula is Gmm over r squared, where r is the distance between the two masses, center of masses. And big G is the universal constant for gravity, which is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Now some people prefer to use mass 1 and mass 2. So if you do that, the formula would be M1, M2. Instead of big M, little m. Okay, so here's example 1. We got the Moon, which orbits the Earth. The Moon has a mass of 7.35 times 10 to the 22 kilograms. And the average distance between the middle of the Earth and the center of the Moon is 384,000 kilometers. The mass of the Earth is 5.98 times 10 to the 24 kilograms. So if we plug it into the formula, Gmm over r squared, we've got big G, 6.67 times 10 to the negative 11, mass of the Earth, mass of the Moon, divided by the distance squared. We get a rather large number of 1.988 times 10 to the 20 newtons. If you do convert that to tons, that's 22,316 trillion tons of force, where a ton is 2,000 pounds. And this provides the orbital motion of the Moon, which has a period of about 29.3 days. So what's the force of gravity on a 50 kilogram person standing on the Earth? Well, the Earth has a radius of 6,380 kilometers approximately, give or take a few, depending on where you're standing. And so in this case here, we got big G, 6.67 times 10 to the negative 11. The mass of the Earth, 5.98 times 10 to the 24. And the mass of our person, 50 kilograms. So if they're standing the surface of the Earth, that's 6,380,000 meters, or 6.38 times 10 to the 6 meters squared. They're going to weigh approximately 489.95 newtons. And the minus sign because it's towards the center of the Earth. That works out to 109.9898 pounds. Now if we use the simple formula that we've been using for years, force of gravity is equal to mg. We got 50 times 9.8. Some people use 9.81. And so that works out to 490 newtons, or 110 pounds. So as you can see, 110 pounds versus 109.9898 pounds, and we're essentially the same answer. We're 99.99% the same. Just a few rounding errors, that's it. Kepler's laws. Now, Newton based his work on the data and laws provided by Kepler. Kepler published 3 laws for planetary motion. The first one is orbits are elliptical. So, for example, the Earth is not actually traveling in a circle. It's almost a circle. The eccentricity is like 0.016. But it is an ellipse. And so, when it's furthest away, that's the aphelion. And when it's closest, the perihelion. And where does helion come from? Well, it comes from Helios, which is the other name for the Sun. Okay, which is also known as Sol. Right? Okay. Kepler worked for another person named Tycho Brahe, who was collecting data for over 20 years. Tycho didn't have a telescope; he had to do it with his eye. So every night he'd go out and write down where everything was located. He originally was trying to prove that Copernicus was wrong. In the end, Kepler and Tycho were able to show that Copernicus was actually probably right. And then Galileo invented really good telescopes that could show other aspects of astronomy weren't really that well known beforehand. So Kepler's second law is that when a planet is moving in orbit, it sweeps out equal areas and equal time intervals. So when it's close, it's moving really fast, but it's at a shorter distance. So this pie shape here is short and wide. When it's far away, it's moving slower, but it's got a longer distance. And what he discovered was the pie shapes, even though they don't look the same, they have the same amount of area in the same time interval. If this is a 1 week time interval, and this is a 1 week time interval, they have the same amount of area. And third, the most important law maybe for Kepler is he discovered the square of the average, the square of the period for the was equal to or proportional to the cube of the average radius. Okay. And using Newton's law, we can actually turn that proportion into an actual equation. So centripetal motion is equal to mass times acceleration. In this case, it's provided by universal gravity. And we're interested in periods, so we're going to use the 4 pi squared r over t squared for our centripetal acceleration. And gravity, of course, is universal gravity, gmm over r squared. Now both sides have an m, and they both have a negative sign, so they cancel out. And we end up rearranging the formula to get t squared equals 4 pi squared over gm r cubed. So it shows that Kepler was right. So if we use this formula on the Earth, just to check to see if it works out well, the Earth's average distance is considered 1 astronomical unit. So the average distance between the Earth and the Sun is called 1 AU, or 1 astronomical unit. And that's approximately 1.495 times 10 to the 11 meters. And the mass of the Sun is 1.99 times 10 to the 30 kilograms. So if we plug that information into the formula, 1.495 times 10 to the 11 meters cubed, and the mass of the Sun, 1.99 times 10 to the 30 kilograms, and then we square root our answer, we do get 31,524,790 seconds, which works out to 364.87 days, or basically 365 days. We're a little bit off just because of rounding errors. Orbital velocity is also very interesting too. How fast is an object when it's moving in a circular orbit? So the Earth's average orbit, once again, is 1 AU, and the Sun's mass, we know that as well. So our centripetal force is going to provide a speed, so speed squared over r. And when we rearrange this, your orbital speed is equal to big G, mass of the object at the center of the circle, divided by the radius. So for the Earth, we're going to have 6.67 times 10 to the negative 11. Mass of the Sun, 1.99 times 10 to the 30, divided by 1 astronomical unit, square rooted. The Earth is moving at 29,800 meters per second, or 29.8 kilometers per second. So almost 30 kilometers every second. At that speed, you could go from Barrie to Toronto in about 3 to 4 seconds. Okay, or if you like miles per hour, that's around 18.5, 19 miles per second, or around Mach 87. Really fast. So in summary, universal gravity, an equation provided by Newton, works everywhere, including on the surface of the planet. And it's, of course, used for orbits. So that's going to be the force of gravity is gmm over r squared, or m1 times m2 if you prefer. Big G, 6.67 times 10 to the negative 11. And a couple formulas we derived is Kepler's third law. Period squared is equal to 4 pi squared over gm r cubed. And the orbital speed is square root of gm over r. I hope this helps. Thank you.